Hello, good afternoon, everyone. Thanks again for joining us to our seminar of the Astronomy Department. Today is our last seminar of this year, so many thanks for participating here. Today we are in the auditorium, but as well through Google Meet and also through our YouTube channel. And today we have the pleasure of having with us Thayse Pacheco. Many thanks, Thayse, for accepting our invitation to be here with us. So let me just introduce a little bit her. She has a bachelor's degree in physics from Universidade Federal de Rio Grande do Sul, a master's degree in astrophysics from Universidade de São Paulo, where she is now a PhD candidate. And recently, Thayse visited the Liverpool John Moores University in the UK. And she is a student representative here at the department, Astronomy Department, and she is involved in outreach activities. And today, Thayse is going to present modeling integrated light spectrum to study hot stellar components in old stellar populations. So as always, please turn off microphones and cameras during the talk. If you have a question, you can raise your hand there in Google Meet. The questions will be done after the presentation. And if you are in the YouTube channel, you can write your question in the chat and we are going to read it for you. So thank you, Thayse. So yours.
Thank you for inviting me. I'm Thayse, I'm a fourth year PhD candidate. I'm working here with Marcos Dias and Paula Coelho. And I'm working with Ricardo Schiavon in UK. We also have collaboration with Lucimara Martins and Ronaldo Levenhagen. And I'm going to talk about our work on modeling integrated light spectrum to study hot stellar components in old stellar populations. So stellar globular clusters are a gravitationally bound group of stars who are distributed mostly in bulge of Milky Way. They are ancient stellar populations where we can study the history formation and the early years of our galaxy. Here I'm showing a beautiful image from Hubble Space Telescope of Omega Centauri, which is one of the biggest globular clusters from Milky Way. And as you can see, we have bluer and redder stars. We can study these stars individually, so we can resolve the core of these globular clusters, of this globular cluster. And to construct the HR diagram, we can use these empirical parameters and separating the stars by colors. We can look at this right plot where we can see the redder stars, which are the coolest stars on the right side, and the hotter stars that are bluer on the left side. And after, we can separate the stars by brightness, where the brightest stars are in the upper part of this image. And here we have an empirical HR diagram, where we can see that the stars are distributed in specific regions. And going to the theoretical plan, we have the HR diagram, where we have the luminosity on the vertical axis and the effective temperature on the horizontal axis, where we have the hottest stars on the left side. And we have, as you can see, the most stars are distributed on the main sequence, and we have a few giant and supergiant stars, and then the star can evolve to the cooling sequence of white dwarfs. We do this when we can resolve the stellar populations, but we can achieve this mostly in Milky Way and for a few objects on Andromeda. Andromeda is the closest galaxy, and as you can see here, we have a lot of globular clusters around Andromeda, but they are unresolved stellar populations. So how can we study these unresolved stellar populations? We have a few ingredients. We need an initial mass function, isochronous, and stellar spectra libraries to build simple stellar populations. And then we can add some star formation ratio and chemical evolution with dust to build a composite stellar population. So we can compare these simple stellar population models to our unresolved observations. So we have with this the integrated light spectrum. Here is an example of NGC 6397, which is one of the most studied globular clusters of Milky Way. And in colored lines, we have WAGS spectra of these globular clusters, and in black lines, we have some simple stellar population fits. On the left side, we have a fit of 12 gigayears, and as you can see, it doesn't fit well. And when we try to fit some simple stellar population to this integrated light spectrum, we have the best fit much younger than we expected. So we need to fix this problem. And here is another example. It's the same spectrum, same WAGS spectra of NGC 6397, and we know that these globular clusters has 13.5 gigayears, but when we try to fit a simple stellar population of this age, it doesn't fit well. So we have an excess on bluer part of the spectrum, and we thought that it can be explained by missing models in the libraries. And our guess is horizontal branch stars, subdwarfs, and or white dwarfs are these missing objects that are bluer objects and old and bluer objects that can fill this excess here on the ultraviolet and bluer part of the spectrum. So going back to the HR diagram, what are these hot subdwarf stars? So after the main sequence phase, they go to the giant phase, and then the helium ignites on the center, and they start going to the horizontal branch, where we have helium burning, center helium burning, and we can see this horizontal branch here, and this extremely horizontal branch here, where it is they are the subdwarfs O and B subtypes. Subdwarfs are stars. We thought that the formation channels are in closed binaries. So we can have an unstable Roach lobe overflow passing through a common envelope to form a short period subdwarf binary. Or we can have an unstable Roach lobe overflow to form some wide binary. And the other unlikely scenario is merge of two white dwarfs, of helium white dwarfs. But this is an emerging study, so we don't know exactly how they are formed. But basically, the star loses all the outermost layers, and the helium core is exposed. So they are mimicking with white dwarfs, and they look like white dwarfs. And going to this color magnitude diagram for neighborhood stars, these are a cross match between Gaia and Lamost, and we can see this a zoom in this region. These are subdwarf candidates, and we have more than 2,000 of subdwarf candidates nearby. So they are. It's important to study this star even in field. But we didn't have models available to study these stars. So we decided to build some atmosphere models and synthetic spectra. And how these models works. So the radiative transfer in stellar atmosphere is basically described by this second order differential equation, where we have a balance between source and sinks. And when the radiation passes through a layer, the radiation can be absorbed, scattered, or re-emitted. And we have some sources contributing to opacity of this layer, which are important to extinction and scattering as absorption coefficients. The mostly models are built in local thermodynamic equilibrium, and the radiative transfer in stellar atmosphere is described by Saha-Boltzmann statistical equilibrium. But we have some limitations here because the kinetic ion excitation, ionization are the same local temperature. And it's not true. So we need to build some more complete models in non-local thermodynamic equilibrium, or non-LTE. The first models were built using just hydrogen, carbon, iron, and a few CNO, silicium, and nickel to contribute for the atmosphere opacity. And we can see important changes on spectrum. So non-LTE metal line blunting effects can see a difference in the line profiles seen in the ultraviolet spectra of hot white dwarfs. And also the lower non-LTE fluxes result from the overpopulation of the hydrogen level at the depth of formation of the continuum flux. hence implying a larger Balmer continuum opacity. And now I'm going to show a few results we published last year. And to build it, our stellar atmosphere models, we used Thayse. Thayse is an open source code, but we can add as many ingredients we want, or our computer can run. And we have these space parameters of log G and effective temperature. We have 4 chemical abundances, and we include all these elements as ions to contribute to the opacity of the atmosphere. And at the end, we have 96 published model and 56 additional models to be published soon. These are all the ions we included for different effective temperatures. We chose these ions considering the ionization energy for each effective temperature. And now talking about the chemical abundances, we have 2 chemical abundances, solar and halo representative abundance, with 2 additional helium abundances. Here I'm showing a figure from late 2019, where we can see helium abundance as a function of effective temperature. These colored points here are observed subdwarfs, and they have these 2 lines here, 2 fits, representing the helium poor abundance and the helium rich abundance. So I choose the helium abundance as a function of effective temperature. And these are our atmosphere structure models comparing LTE and non-LTE models. So here we have the temperature as a function of mass depth, where we have these colors are the effective temperature pattern. So we have the hottest models upper and the coolest models down. And this left part is the upper atmosphere, and this right part is the inner atmosphere. We don't see much difference in the inner atmosphere, but we have we can see that the LTE models are isotherms on the upper atmospheres, and the non-LTE models have some temperature inversions, like we can see here. And this region is an important region to line formation, so it's the reason it's really important to consider non-LTE effects. Here are some structure models to electron density upper and to mass density down. So we can see for these coolest models, this little inversion here, which is the convective zone we used to 10,000 Kelvin models. We also have this English-Steller diagram, which is showing the electron density at this depth as a function of number of Balmer lines we can see, and as the most gas is the most hydrogen is ionized for the hottest stars, we almost can't see the Balmer lines for the hottest stars. Now talking about the spectral synthesis, we used SynSpec to compute our spectral synthesis. SynSpec is also open source code. We covered our wavelength between 1,000 and 10,000 angstrom, and we included hydrogen and hydrogenic lines, quasi-molecular satellites of Lyman alpha, Lyman beta, and age alpha. We also included helium triplet lines and helium-2 lines as an approximation of hydrogenic ion by Stark and Doppler profile, and also we included Stark broadening tables. Finally, we run routing using microturbulence velocity of 10 kilometers per second with no rotation and no instrumental broadening. These are a few examples of our synthetic spectra in continuum, showing the continuum, and showing the Balmer discontinuity. Here we are showing a comparison with observations in optical region. These purple lines are observed spectra by Lamoste, and we have 25,000 Kelvin and a 45,000 Kelvin. Comparing with this observation, we have a fair agreement between observed and model spectra. We also have this comparison with observation in ultraviolet. And finally, we computed some synthetic magnitudes. Here I'm showing two examples of Hubble Space Telescope and stronger color diagrams. And on the left side, we can see the continuum inclination here, and we can see the Balmer discontinuity in these color diagrams, with an important split by surface gravity on hotter models. And we also compared our synthetic magnitudes with slow and digital sky survey data. And here I'm showing a color diagram composed by observational data on subdwarfs. And these small crosses and dots are observed, color. And the colored dots are colors with determined surface temperature, and these bigger points are our synthetic magnitudes. And we can see that our synthetic magnitudes is in fair agreement with this branch of this color diagram, and with this the branch for single subdwarfs. And we have this upper branch here, which is the subdwarfs in binary systems. You can download our models in Spec Models website, Vizier, or Spanish Virtual Observatory, or you can just send me an email and I can send you the spectra. And now we are moving to stellar population analysis. And the question we need to answer is how much do hot, low mass stellar components contribute to the integrated light of old stellar population? And here I'm showing a beautiful image of NGC 2808 as a proxy of old galactic globular cluster with an extremely horizontal branch. And here we are showing a color magnitude diagram using Hubble Space Telescope photometric data. And we separated the stars. We separated the stars by evolutionary phase. So we have in yellow the main sequence, in cyan the giant and supergiants, in red the red clump, in blue the blue stragglers, in purple the horizontal branch, and in magenta the extreme horizontal branch or subdwarf stars. Having this stellar population separated, we can match its star, its color observed to a model by k nearest neighbors in 10 dimensions. So here I'm showing a few examples, but we can compose 10 colors using Hubble Space Telescope photometric data. So after to match its star to a model by KNN, we can build our simple stellar population. And here I'm showing a simple stellar population synthesis of NGC 2808. And this is a flux as a function of wavelength, and each spectra is one of the stellar population I colored in that color magnitude diagram I showed before. So we have the giant stars and the main sequence stars dominating the light, but we have an important light of horizontal branch in purple and extremely horizontal branch stars going through blue and ultraviolet. And after, as we have this simple stellar population synthesis to each evolutionary phase, we can quantify how much each one are contributing to integrated light spectrum. So here I have a synthetic integrated light spectrum basic, which is composed by main sequence, giant, and red clump stars. And then I can estimate how much the inclusion of blue stragglers or blue horizontal branch or extreme horizontal branch are contributing to the total spectrum. And we can estimate that the blue stragglers are contributing with 1% in this region, in this bluer region. Subdwarfs are contributing with almost 4%, and horizontal branch are contributing with 20%. And when we sum the three hot populations to the spectrum, we have a contribution of 25% in this region. So it's really important to take in account these hot stellar populations to build this, to study integrated light spectrum. And we also are modeling integrated light spectrum to study hot stellar populations in node stellar populations. And here I'm showing another globular cluster, which is NGC 7089 or M2. And again, we are looking at the color magnitude diagram, and we separated the evolutionary phases in this galactic globular cluster with an extreme horizontal branch. So again, we have main sequence in yellow, giant and supergiants in cyan, blue stragglers in blue, horizontal branch in purple, and subdwarfs in magenta. And here we considered the photometric completeness of this sample, and I'd like to show you different color magnitude diagrams in different bands. So we mostly see these color magnitude diagrams in optical or infrared, and in this case, the giant stars are dominating the light of the globular cluster. But when we look at the blue and ultraviolet color magnitude diagram, like this on the right, we can see that horizontal branch and subdwarfs or extreme horizontal branch are dominating the light of the globular cluster. So again, we did a match between each observed color to a model, and we build the simple stellar population synthesis for each evolutionary phase. And here we have a wide range of wavelength, and we can see that when we look at the ultraviolet, the light from giant stars in cyan and main sequence stars in yellow are almost zero. And as we see on these previous color magnitude diagrams, the light from horizontal branch and extreme horizontal branch are dominating the light of the spectrum. Then we can sum all these simple stellar populations to build a synthetic integrated light spectrum, and we can compare with observations. And here I'm showing the spectra from UA, the International Ultraviolet Explorer, in orange, green, and blue. And we also have in gray the WAGS spectrum. And finally, in magenta, we have our modeled integrated light spectrum for M2. And I think this is beautiful. We have a great agreement between observed and model spectra. And this was the first time this integrated light spectrum were modeled in this level of details. So why do we study integrated light spectrum of old globular clusters? With this, we can improve stellar population synthesis models. We can infer ages in a more reliable way. And we also can break the degeneracy between age and horizontal branch morphology. But at the end, next year, our next step is expand our analysis to verify the impact of these hot stellar components on extragalactic studies. We are going to study some globular clusters of Andromeda. And just to summarize, I presented a grid of synthetic spectra for subdwarfs built in non-LTE line blanketed atmosphere models. We also have a high resolution spectral synthesis performed from ultraviolet to the near infrared. And the hot components as subdwarfs, blue horizontal branch stars, and blue stragglers contribute with 25% of the light in the near ultraviolet band. And the horizontal branch and the extreme horizontal branch dominate the light in the far ultraviolet band. And finally, for the first time the integrated light spectra of a globular cluster were modeled in this level of detail from ultraviolet to infrared to optical and infrared range. So if you have any comments or questions, I'll be happy to answer you.
Thank you. Thank you very much for your talk. I don't know if you can hear me. Yes? Okay. Okay, so let's, I will start with a question first, if I may. You mentioned that when you were calculating your theoretical spectra, you were considering zero rotational velocity. Is this the case? So if so, the impact on the results would be due to the mixing. Can you comment on this?
About the velocity, you can see these effects when you are comparing your spectra with a stellar spectra. But when we are seeing the integrated light spectrum, this is a relevant effect.
Okay. Okay, thank you.
You're welcome.
Okay, yes.
Thank you, Thayse, for the talk. Very clear and didactic. I have think they are very simple questions. In the beginning, you were motivated to build, to explain this observational spectrum for this globular cluster, no resolved globular clusters, with single age population of stars, right? So to include, I don't know if it's usual to include multiple populations, multiple ages populations to try to overcome this disparity in the fitting of the different parts of the spectrum.
Yes, we usually use some different evolutionary phases, but the libraries have basically main sequence and giant stars. And we didn't have included these hottest components. So the evolved light, the light from evolved stars are mimicking with these upper blue massive stars on main sequence.
Right. But all the stars of this population were born more or less at the same time.
Yes, yes.
Ah, okay. Okay, no. I have another question. I'm curious, when you showed some examples in the beginning of your talk, and also in the slide 42, we can see some emission lines from the spectra, and this is not captured by the synthetic models. Could you explain for us why?
We have one emission line here. The other one, these ones are just bound effects of the spectra. We have this one emission line, which isn't real. We have this is Lyman alpha, and this is due to the solar radiation in solar system. So when we observe, we have this background effect from solar radiation.
Thank you. Also in the optical sides, they're not relevant to the emission lines that appear.
Yeah.
Okay. And I have a last question, if I can. In the beginning, you also mentioned that for doing this modeling, you need to assume, I don't know, to calibrate some dusty model. This is to remove the foreground, or this is something inside the cluster?
This is when you are computing a composite stellar population. Here we are doing simple stellar population, so we didn't do this. But when you add some star formation ratio and dust, when you are studying galaxies, it's important.
Ah, okay. Not it for some globular cluster in the Milky Way.
Yeah.
Okay. Thank you.
You're welcome.
Somebody has another question, some comments? Yeah.
So the fraction that of extreme stars that you find in the globular cluster is compatible with what we expect from stellar evolution?
I think so. Yes. Yes.
Okay. So, there's more comments or more questions? No? Okay, so thank you very, very much for your presentation, for showing your work to us. Do you want to say something?
No, thank you for inviting me. I'm happy to be here.
Okay, thank you very much, and
Thank
all
you.
the best for all your future work. And okay, I would like to thank everyone who was joining us and participating in our seminars. And well, see you next year. Thank you very much.